An efficient electric architecture for success relies on multiple components. One of them is the efficiency filter, which offers notable benefits to power-intensive companies in particular. The handover point of the energy provider is the transformer station. The energy provider delivers the energy through the red cable to the medium voltage transformer. From there, the transformed energy goes into the low voltage main distribution. Right after the medium voltage transformer, the efficiency filter is installed. The main component of the efficiency filter is a specially designed three-phase transformer. First, let's begin with the present state and initially disregard the efficiency filter. A classic setup of a power supply to the building consists of a medium voltage transformer, a main switch, a 4-wire feed, the three phases L1, L2, and L3, and the neutral conductor, which is represented here in blue. The main switch is closed. The power can now flow. In the individual phases, different currents are formed, represented here by arrows of different sizes, which lead to an asymmetric load. As a result, a current component is generated on the neutral conductor. This current flows in the opposite direction back to the medium voltage transformer. Some of the backflow can also follow the route through additional grounded system components apart from the original path it took. All in all, this leads to electrical losses that don't bring any benefit, but still have to be paid for. Ideally, these are zero. Let's take a step back and look directly from above at the main windings U, V, and W, which are depicted in red color. Each winding sits on one of the three legs of the iron core and is represented by its main connections, input and output. Let's start with installing the efficiency filter. He's going to be installed in the main line in series. The neutral conductor remains untouched. He will not be interrupted. Only the three phases are connected with the windings through the input and output connections. The main switch is being closed. The ladder currents are now flowing through the main winding. Already now, the main developments feel like a drag. We limit the inrush currents and dampen the harmonics, according to the function of a choke coil. But this well-known technique doesn't seem to work against asymmetric loads on the power grid. There is still a current flow on the neutral conductor, going back into the medium voltage transformer. A crucial aspect of our three-phase reactor is the iron core, which enables the balancing of asymmetric loads by leveraging the magnetic field's capabilities. As is customary with iron core reinforced throttles, the inductance is also increased here. This increases the energy storage capacity so that the voltage can be better supported during short-term voltage fluctuations. Simple electrophysics and technology that has been well known and proven for a multitude of years. Now we are going to add an additional feature to the throttle. This well-known and established technique is still utilized today for a variety of applications. Utilized primarily in the context of industrial applications as a scatter field transformer for various practical purposes. By increasing the surface area of the coil, we are able to obtain additional well-defined gaps in the air. The layout was selected in a manner that ensures an ideal balance between the requirements for space and functionality. In this way, the geometry changes only in one dimension. The filter can be built more compact overall. In the subsequent step, a spacer plate is inserted into every air gap for the purpose of mechanical stabilization. These increase the mechanical strength, especially when strong forces occur, such as in short circuits in the power grid. Depending on the rated current size of the choke, the number of air gaps also varies, as well as the sizing of the spacer plates. By adding more surface area, we increase the inductance even further, and also generate a significant amount of stray field with increased magnetic resistance. This technique has proven itself especially in the operation of power electronics. High-frequency components are attenuated, and the effects of rapid changes in current are significantly reduced, even under heavy current load. This method is still utilized today in the form of stray field transformers, for instance in the field of railway technology and its various applications. In addition to the primary winding just described, A second secondary winding is applied directly to the core, which is shown in blue color. This one is also equipped with additional air gaps. Setup same as main winding. Secondary winding, electrically speaking, still galvanically separated from primary winding, but already magnetically coupled to primary winding through core. In order to decrease the voltage drop caused by the main winding, the direction of the winding is reversed in this case, as per the principle of the transformer. When current passes through the main winding, a voltage proportional to the main current is already generated in the secondary winding. To manipulate the secondary coil, 6 aluminum contacts are connected at different positions. The inner and outer contact is comprised of all turns, with each of the intermediate contacts only tapping a portion of the secondary winding coil. That way you can choose different translation ratios between the primary and secondary winding. Let's quickly summarize the design at this point. The combination of primary and secondary windings, as well as the additional air gap with its spacer plates, which are guided by a common 3-legged iron core, form a combination of a series choke and a stray field transformer, technologies that initially don't differ from the already long-established designs. And in terms of functionality, there are initially no significant differences compared to proven technologies. This combination leads to a higher network quality and, as a result, also to an improved efficiency. You can already reduce electrical energy losses. So far, however, everything has been designed for use in symmetrically loaded power grids. Alright, let's get started with the tweaks to the technology that make up our efficiency filters. First, we connect the inner end of the secondary coil to the input of the main winding. This is transformed into a brand new hub that carries the backflow of the 3 secondary coils. Thus, we remove galvanic isolation between primary and secondary windings. As seen, asymmetrical conductor currents through main coil remain unchanged for now. The impact of the efficiency filter remains unaltered. Another vital modification to our efficiency filter is the establishment of an extra floating star point, which is implemented without a connection to a neutral conductor. The 3 secondary windings are combined in the floating star point via the external aluminum contacts. And here lies a crucial innovation leap of our efficiency filter. The floating star point is currently not connected to the neutral conductor and can therefore assume different potentials depending on the load, which result from different phase loads and the opposite winding direction. Once the efficiency filter is turned on, the star point protection also closes. The 3 secondary coils are connected to each other via the star point and return to the junction point at the input of the efficiency filter through the other end of the coil. Now, the induction of the main winding also affects the secondary winding, driving a current through it. Now, the current of the secondary coil adds to the main current. By winding the secondary coil in the opposite direction to the current component and main winding, a total current is created. When there is an unbalanced load due to the shifting of the floating neutral point, this can counteract the imbalance and restore balance. Pretty straightforward and well-known electrophysics. Because the primary current and the current of the secondary coil must always combine to form the total current in the end. The Kirchhoff's rule applies here as well. This means that less neutral current will flow back to the medium voltage transformer. Electric energy losses that have to be paid for, but bring no benefits. In order to adjust the effects to their local conditions, it is possible to adjust the winding conditions by means of the aluminum contacts of the winding taps of the secondary coil in different ways. When activating the efficiency filter, we begin with the maximum windings of the secondary coil, thus minimizing the counterflow component. Depending on the choice of winding ratio, a current component in the range of 4 to 10% of the supply current flows. This flows over the star point protection, and depending on the unbalanced load, back to the input of the efficiency filter, where it counteracts the asymmetry. Now let's examine the effects shown together. You can identify the primary current component depicted in green, the stray fields in magenta, generated by the air gap, the opposing current component of the secondary winding in blue, which is sent back to the input of the main coil via the winding tap and the newly introduced floating neutral point. You can make adjustments to the winding ratio by using the different taps on the secondary coils. So the inductance and the stray field component, clearly visible in the color magenta, are increased or decreased, thus varying the effect of the star point displacement. The crucial thing is the simultaneity of all effects, which always act simultaneously through the construction of the efficiency filter. In a nutshell, the efficiency filter consists of a combination of well-known and proven electrophysics, built from simple and familiar materials like the iron core, insulating paper, aluminum, spacer plates, and taking advantage of the simultaneity factor. These effects, when cleverly managed, significantly enhance the efficiency in the power grids of today, which exhibit mostly non-linear behavior. The bypass integrated in the efficiency filter has two essential functions: the reliability and timing in efficiency measurement. One challenge was the uninterrupted bridging of the throttle with a bypass system. When there are changes in the local network, like disruptions on the medium voltage side or in case of overload, the efficiency filter auto switches to bypass mode. For the validated ECV measurement method, an automated and remote-controlled bypass system was developed in collaboration with the manufacturer of the circuit breaker. The bypass switch can be switched between saving and bypass operation every 300 seconds, with a current of up to 4,000 amperes. The asymmetrical leakage currents and the heightened neutral currents in bypass mode can be clearly seen and easily observed. The current flows in green in saving mode. In total, there are 288 switch circuits that are controlled within a span of 24 hours, ensuring that a change of operation occurs every 5 minutes throughout the day. With the resulting intervals of saving and bypass, the ECV measurement method can be carried out to measure the increase in efficiency and the reduced kilowatt hours. Why not also prioritize energy efficiency and our network expertise? Contact us. We anticipate your presence.